Autonomous boats can target and latch onto each other. The city of Amsterdam envisions a future where fleets of autonomous boats cruise its many canals to transport goods and people, collect trash, or self-assemble into floating stages and bridges. To further that vision, MIT researchers have given new capabilities to their fleet of robotic boats, which are being developed as part of an ongoing project that let them target and clasp onto each other, and keep trying if they fail. About a quarter of Amsterdam's surface area is water, with 165 canals winding alongside busy city streets. Several years ago, MIT and the Amsterdam Institute for Advanced Metropolitan Solutions (AMS Institute) teamed up on the rowboat project. The idea is to build a fleet of autonomous robotic boats, rectangular hulls equipped with sensors, thrusters, microcontrollers, GPS modules, cameras, and other hardware, that provides intelligent mobility on water to relieve congestion in the city's busy streets. One of project's objectives is to create rowboat units that provide on-demand transportation on waterways. Another objective is using the rowboat units to automatically form pop-up structures, such as footbridges, performance stages, or even food markets. The structures could then automatically disassemble at set times and reform into target structures for different activities. Additionally, the rowboat units could be used as agile sensors to gather data on the city's infrastructure, and air and water quality, among other things. In 2016, MIT researchers tested a rowboat prototype that cruised around Amsterdam's canals, moving forward, backward, and laterally along a pre-programmed path. Last year, researchers designed low-cost, 3D-printed, 1/4 scale versions of the boats, which were more efficient and agile, and came equipped with advanced trajectory tracking algorithms. In a paper presented at the International Conference on Robotics and Automation, the researchers describe rowboat units that can now identify and connect to docking stations. Control algorithms guide the rowboats to the target, where they automatically connect to a customized latching mechanism with millimeter precision. Moreover, the rowboat notices if it has missed the connection, backs up, and tries again. The researchers tested the latching technique in a swimming pool at MIT and in the Charles River, where waters are rougher. In both instances, the rowboat units were usually able to successfully connect in about 10 seconds, starting from around 1 meter away, or they succeeded after a few failed attempts. In Amsterdam, the system could be especially useful for overnight garbage collection. Rowboat units could sail around a canal, locate and latch onto platforms holding trash containers, and haul them back to collection facilities. In Amsterdam, canals were once used for transportation and other things the roads are now used for. Roads near canals are now very congested, and have noise and pollution, so the city wants to add more functionality back to the canals, says first author Luis Mateos, a graduate student in the Department of Urban Studies and Planning (DUSP) and a researcher in the MIT Sensible City Lab. Self-driving technologies can save time, costs and energy, and improve the city moving forward. The aim is to use rowboat units to bring new capabilities to life on the water, adds co-author Daniela Russ, director of the Computer Science and Artificial Intelligence Laboratory (CSAIL) and the Andrew and Erna Viterbi Professor of Electrical Engineering and Computer Science. The new latching mechanism is very important for creating pop-up structures. Rowboat does not need latching for autonomous transportation on water, but you need the latching to create any structure, whether it's mobile or fixed. Joining Mateos on the paper are, Wei Wang, a joint postdoc in CSAIL and the Sensible City Lab, Banti Ganetti, a graduate student in the Department of Electrical Engineering and Computer Science, Fabio Duarte, a DUSP and Sensible City Lab research scientist, and Carlo Ratti, director of the Sensible City Lab and a principal investigator and professor of the practice in DUSP. Making the connection. Each rowboat is equipped with latching mechanisms, including ball and socket components, on its front, back, and sides. The ball component resembles a badminton shuttlecock, a cone-shaped, rubber body with a metal ball at the end. The socket component is a wide funnel that guides the ball component into a receptor. Inside the funnel, a laser beam acts like a security system that detects when the ball crosses into the receptor. That activates a mechanism with 3 arms that closes around and captures the ball, while also sending a feedback signal to both rowboats that the connection is complete. On the software side, the rowboats run on custom computer vision and control techniques. Each rowboat has a lidar system and camera, so they can autonomously move from point to point around the canals. Each docking station, typically an unmoving rowboat, has a sheet of paper imprinted with an augmented reality tag, called an April tag, which resembles a simplified QR code. Commonly used for robotic applications, April tags enable robots to detect and compute their precise 3D position and orientation relative to the tag. Both the April tags and cameras are located in the same locations in center of the rowboats. When a traveling rowboat is roughly 1 or 2 meters away from the stationary April tag, the rowboat calculates its position and orientation to the tag. Typically, this would generate a 3D map for boat motion, including roll, pitch, and yaw, left and right. But an algorithm strips away everything except yaw. This produces an easy-to-compute 2D plane that measures the rowboat camera's distance away and distance left and right of the tag. Using that information, the rowboat steers itself toward the tag. By keeping the camera and tag perfectly aligned, the rowboat is able to precisely connect. The funnel compensates for any misalignment in the rowboat's pitch, rocking up and down and heave vertical up and down, as canal waves are relatively small. If, however, the rowboat goes beyond its calculated distance, and doesn't receive a feedback signal from the laser beam, it knows it has missed. In challenging waters, sometimes rowboat units at the current 1/4 scale are not strong enough to overcome wind gusts or heavy water currents, Mateos says. A logic component on the rowboat says, "You missed, so back up, recalculate your position, and try again." Future iterations. The researchers are now designing rowboat units roughly 4 times the size of the current iterations, so they'll be more stable on water. Mateos is also working on an update to the funnel that includes tentacle-like rubber grippers that tighten around the pin, like a squid grasping its prey. That could help give the rowboat units more control when, say, they're towing platforms or other rowboats through narrow canals. In the works is also a system that displays the April tags on an LCD monitor that changes codes to signal multiple rowboat units to assemble in a given order. At first, all rowboat units will be given a code to stay exactly a meter apart. Then, the code changes to direct the first rowboat to latch. After, the screen switches codes to order the next rowboat to latch, and so on. It's like the telephone game. The changing code passes a message to one rowboat at a time, and that message tells them what to do, Mateos says. The research was funded by the AMS Institute and the City of Amsterdam. Was Mona Lisa's smile a lie? Mona Lisa's smile has intrigued humanity since famed artist Leonardo da Vinci painted the portrait in the early 16th century. A research team that includes a University of Cincinnati (UC) neurologist now says that her smile was non-genuine because of its asymmetry. Our results indicate that happiness is expressed only on the left side. According to some influential theories of emotion neuropsychology, we here interpreted the Mona Lisa asymmetric smile as a non-genuine smile, also thought to occur when the subject lies, the authors write in their study published recently in the April 2019 issue of the journal Cortex. Luca Marsili, MD, PhD, an instructor in neurology and rehabilitation medicine at the UC College of Medicine, was the lead author of the paper. Marsili and his colleagues Lucia Ricciardi, MD, PhD, with St. George's University of London, and Matteo Bologna, PhD, of the Sapienza University of Rome, asked 42 people to judge which of 6 basic emotions were expressed by 2 chimeric images of the left and right sides of Mona Lisa's smile. A chimeric image is a mirror image of, in this case, just one side of the smile. 39, or 92.8%, of the raters indicated that the left half of the smile displayed happiness while none indicated the right side showed happiness. In assessing the right side smile, 35 said the expression was neutral, 5 said it was disgust and 2 indicated sadness. The authors also point out that there also is no upper face muscle activation in the Mona Lisa painting. A genuine smile causes the checks to raise and muscles around the eyes to contract, and is called a Duchenne smile, after 19th-century French neurologist Guillaume Duchenne. The asymmetric smile, also known as a non-Duchenne smile, reflects a non-genuine emotion and is thought to occur when the subject lies, the authors note. Considering it is unlikely that a person who sits motionless for hours to be painted is able to constantly smile in genuine happiness, the simplest explanation is that the Mona Lisa asymmetric smile is the manifestation of an untrue enjoyment, in spite of all the efforts that Leonardo's jesters used to make in order to keep his models merry, the researchers write. An alternative intriguing possibility, however, is that Leonardo already knew the true meaning of asymmetric smile more than 3 centuries before Duchenne's reports and deliberately illustrated a smile expressing a non-felt emotion. If Da Vinci was aware of the meaning of an asymmetric smile, the authors speculate that Mona Lisa's smile might hide cryptic messages, for example, that this was in reality a self-portrait or that the portrait referred to a man or a dead woman. While the Mona Lisa smile continues to attract attention of its observers, the true message it conveys remains elusive and many unsolved mysteries remain to be elucidated, perhaps via the knowledge of emotion neuropsychology, the researchers conclude. This research did not receive any specific grant from funding agencies in the public, commercial or not-for-profit sectors. Time travel feature added to drives to fight ransomware attacks. One of the latest cyber threats involves hackers encrypting user files and then charging ransom to get them back. In the paper, Project Almanac, a time-traveling solid-state drive, University of Illinois students Chance Coates and Xiaohao Wang and assistant professor Jian Huang from the Coordinated Science Laboratory look at how they can use the commodity storage devices already in a computer to save the files without having to pay the ransom. The paper explains how we leverage properties of flash-based storage that currently exist in most laptops, desktops, mobiles, and even IoT devices, said Coates, a graduate student in Electrical and Computer Engineering (ECE). The motivation was a class of malware called ransomware, where hackers will take your files, encrypt them, delete the unencrypted files and then demand money to give the files back. The flash-based, solid-state drives Coates mentioned are part of the storage system in most computers. When a file is modified on the computer, rather than getting rid of the old file version immediately, the solid-state drive saves the updated version to a new location. Those old versions are the key to thwarting ransomware attacks. If there is an attack, the tool discussed in the paper can be used to revert to a previous version of the file. The tool would also help in the case of a user accidentally deleting one of their own files. Like any new tool, there is a trade-off. When you want to write new data, it has to be saved to a free block, or block that has already been erased, said Coates. Normally a solid-state drive would delete old versions in an effort to erase blocks in advance, but because our drive is keeping the old versions intentionally, it may have to move the old versions before writing new ones. Coates described this as a trade-off between retention duration and storage performance. If the parameters of their new tool are set to maintain data for too long, old and unnecessary versions will be kept and take up space on the storage device. As the device fills with old file versions, the system takes longer to respond to typical storage requests and performance degrades. On the other hand, if the parameters are set to a retention window that is too narrow, users would have a quicker response time, but they may not have all of their backup files saved should a malware attack take place. To manage this trade-off, Huang and his students built in functionality for the tool to monitor and adjust these parameters dynamically. Despite the dynamic changes to system parameters, their tool guarantees data will be retained for at least 3 days. This allows users the option to back up their data onto other systems within the guaranteed time period if they choose to do so. The idea behind their tool has gained interest at an international level. The paper about this research was published at a top-tier system conference, Eurosys, this past spring. Coates represented the group at the conference. Our research group really enjoys building practical computer systems. This is a great practice for our students. They will experience how our research will generate real-world impact, said Huang, an assistant professor of electrical and computer engineering at Illinois. Moving forward, our group will look at the possibility of retaining user data in a storage device for a much longer time with lower performance overhead, and applying the time-traveling solid-state drive to wider applications such as systems debugging and digital forensics. Seeing disfigured faces prompts negative brain and behavior responses. People with attractive faces are often seen as more trustworthy, socially competent, better adjusted, and more capable in school and work. The correlation of attractiveness and positive character traits leads to a beautiful as good stereotype. However, little has been understood about the behavioral and neural responses to those with facial abnormalities, such as scars, skin cancers, birthmarks, and other disfigurements. A new study led by Penn Medicine researchers, which published today in Scientific Reports, uncovered an automatic disfigured as bad bias that also exists in contrast to beautiful as good. Judgments on attractiveness and trustworthiness are consistent across cultures, and these assumptions based on facial beauty are made extremely quickly. On the other hand, people with facial disfigurement are often targets of discrimination, which seems to extend beyond the specific effects of lower overall attractiveness and may tie in more with the pattern of results with stigmatized groups, said the study's lead author Anjan Chatterjee, MD, a professor of neurology, and director of the Penn Center for Neuroaesthetics. In order to right any discrimination, the first step is to understand how and why such biases exist, which is why we set out to uncover the neural responses to disfigured faces. Neuroimaging studies show that seeing attractive faces evokes brain responses in reward, emotion, and visual areas compared to seeing faces of average attractiveness. Specifically, attractive faces evoke greater neural responses as compared to faces of average attractiveness in ventral occipito-temporal cortical areas, which process faces and other objects. Additionally, attractiveness correlates with increased activations in the anterior cingulate cortex and medial prefrontal cortex, areas which are associated with rewards, empathy, and social cognition. The researchers set out to evaluate the behavioral and brain reactions to disfigured faces and investigate whether surgical treatment mitigates these responses. In 2 experiments, the researchers used a set of photographs of patients with different types of facial anomalies, before and after surgical treatment, to test whether people harbor a disfigured as bad bias and to measure neural responses. In the first experiment, a behavioral study with 79 participants, the researchers tested if people harbor implicit biases against disfigured faces and if such implicit biases were different from consciously aware, self-reported explicit biases. The behavioral experiment consisted of an implicit association test (IAT) and an explicit bias questionnaire (EBQ) to identify whether people have a negative bias for disfigured faces. For the IAT, the researchers used the set of before and after photographs as a stimulus. The EBQ consisted of 11 questions which query conscious biases against people with facial disfigurements. While the team found no indication of an explicit bias, they found that non-disfigured faces were preferred in the IAT. This bias was particularly robust for men. In a follow-up functional MRI (fMRI) study with 31 participants, researchers tested brain responses to the same picture pairs. Participants judged the gender of each photograph they viewed. The researchers found increased neural responses in visual regions of the brain, the ventral occipito-temporal cortical areas, and decreases in regions associated with empathy, the anterior cingulate and medio-prefrontal cortex. In sum, the authors found that people have implicit negative biases against people with disfigured faces, without knowingly harboring such biases. The diminished neural responses in the anterior cingulate cortex suggests that people are less empathetic when looking at individuals with disfigurement. This is also a potential neural marker of dehumanization, as diminished neural responses in the anterior cingulate cortex is also observed in response to other stigmatized people, such as the homeless and drug addicts. The emphasis of attractiveness and its association with positive attributes highlights the pervasive effect of appearance in social interaction. Chatterjee said. While we found that corrective surgery mitigates negative social and psychological responses to people with facial anomalies, we are also exploring alternative strategies to minimize bias towards people with facial conditions. This work was supported by the Penn Center for Human Appearance and the Global Wellness Institute.